morning everybody. So, today we will start with oscillatory reactions. Okay. So, before going into the details of it, let us talk about what is autocatalysis. Again we would just like to recapitulate. Now, in case of autocatalytic reaction, it is a commonly observed case is reaction of permanganate with oxalic acid. So, initially the color of permanganate does not decolorize fast. So, what is happening under warm condition, if you add permanganate in oxalic acid solution, it persists for some time, and then after some time, means maybe after 30 seconds or so, the moment what is happening, that the moment you add more of permanganate, the color disappears fast. So, this happens because of the formation of your manganese ion. Initially there was no manganese ion, but the moment it is generated, it catalyzes, it acts as the autocatalyst for the reaction. So, the product of reaction helps accelerating the rate of reaction for your autocatalysis. So, what is happening, that A giving rise to product, and this product again along with A is involved in the rate expression. So, that is your A giving rise to product. Okay, this product is again used up. So, rate is equal to K into A into P. So, initially since product is very small, so rate is small, that is lower rate. At the moment this is built up, so its concentration is appreciable, and as a result of which rate is increased. Okay. The rate suggests the equation that A plus P giving rise to P plus P. The mechanism is A to P is an initiation step, and then A plus P giving rise to P plus P is the autocatalytic step. That is, this one is again used up over here. Okay, used up over here. Oscillatory reaction, when having two or more autocatalysis steps, then we can get oscillatory reaction. That is, A plus X giving rise to X plus X, X plus Y giving rise to Y plus Y, third Y is giving rise to something else B. Okay. So, basically one, two or more autocatalytic step, if it is there, then we can get oscillatory situation. So, the corresponding rate expressions are like this. Okay. After the reaction starts, X increases exponentially, okay, due to autocatalysis step, that is step 1. And in presence of X, okay, the second reaction starts, okay, and results in Y. Y again increases exponentially due to autocatalysis, and because of step 2, which consumes X, so decrease, so X decreases from maximum value as Y is high. Okay. When X is lowered, autocatalysis step, X is lower, autocatalysis in step 2 is not important, and Y follows X to a lower value. Okay. So, you see X initially builds up, then it decreases, and Y after some time it is going up, that is Y is following X. Okay. You see X is oscillating, Y is oscillating, but there is a phase difference. Okay. So, this way it is happening. Now, here we will talk about this history and also the mechanism. One is Briggs-Rauscher reaction, another is Belousov-Zhabotinsky reaction, one is BR reaction, another is BZ reaction. BR and BZ reactions are are two of the most commonly demonstrated oscillating reactions. Okay. Br reaction, it is a colorless liquids are mixed to form an amber solution, that is the basic description, which turns to blue black color and periodically goes back and forth between two colors. And Bz reaction, the reaction mixture revolves through green, blue, purple and red colors. Okay, so color wise there are 4 colors over here, and here amber to blue black. Now the chemists involved in such studies, B.P. Beluzov was a Russian chemist in 1950s attempting to study Krebs cycle and discovered the oscillatory reaction, and he sent this manuscript to a journal, and it was eventually rejected. His manuscript was rejected. Okay, the grounds on the grounds that it is impossible, it cannot happen, because conventional opinion of the time, that is the then understanding, was that all reactions should proceed to thermodynamic equilibrium. So there is no way that the reaction can revert back. So this oscillation is not in harmony with the then thermodynamic understanding. I mean, people never thought of such reaction, I mean never can imagine. Okay. So conventional idea is that why the reaction will get back to another, I mean color should get back to the initial, and then initial will again go to the final, and final again back to initial. Why should it happen? So that's why his manuscript was rejected. Okay. And Beluzov was so offended by such a rejection. Actually, he was quite sure that this is a real observation, there is nothing wrong in it. So he was so frustrated due to this rejection, and he left science forever. Okay, he never tried anything because he will think that, I mean, he was so frustrated. Now, biochemistry professor Schoenl and took up Beluzov's reaction. Under Schoenl and Zhabotinsky investigated the mechanism and spatial distribution patterns of the reaction. Okay. So it is the Zhabotinsky who, under the guidance of Schoenl, they studied this reaction. Later on, Berry and others in UC Berkeley described first homogeneous isothermal chemical oscillation, in 1921. Okay, and later on means not in 1950, before 1950, in 1921, and this was ignored by scientific journals for many years. Means before Beluzov, the first description of homogeneous isothermal chemical oscillation was in 1921 by Berry and others. Levavsky, okay, Berry and Levavsky. Then later on, in later time, Briggs and Rauscher in Galileo High School in San Francisco investigated Berry reaction at UC Berkeley. Combine parts of Berry reaction with parts of BZ reaction to have their own BR reaction. Okay, that is Briggs Rauscher reaction. So Briggs Rauscher reaction, that is BR reaction, 3 solutions are mixed. Solution 1, that is A, is 4 molar H2O2, B is 0.2 molar potassium iodate KiO3 and 0.77 molar H2SO4, that is solution B. And the third one is 0.15 molar malonic acid and 0.02 molar MnSO4. These are the 3 solutions, and spiked with 1% starch solution. That is an indicator. Very little amount of starch solution has been added there. Okay, starch is an indicator. So starch is an indicator. If iodine is liberated, so it becomes blue or blue black. Okay. So a reaction scheme is like this: non-radical reduction of iodate to hypoiodous acid. Okay. So if there is an abundance of iodide ion, the following reactions will take place. There are 3 steps like this: IO3 minus plus I minus plus in presence of an acid, giving rise to HiO2 plus HOI, then HiO2 plus I minus plus H plus, giving rise to hypoiodous acid. Okay. Then giving rise to HOI plus H2O2, giving rise to I minus plus O2 plus H plus and water. Okay. So net reaction is iodate plus H2O2 plus H plus, giving rise to HOI plus 2O2 plus 2H2O. Then this hypoiodous acid HOI reacts with malonic acid. Malonic acid is CH2 CO2H whole 2, that means it is a dicarboxylic acid. Okay. So it is iodination of this on this carbon, that is CH2 carbon, and then as HOI is consumed in the reaction 5, you see here it is consumed, the I minus from reaction 3, this one decreases, and reaction 1 2 slows down greatly. This one, these two are slowed down greatly. Okay. So when I minus is low, the radical reduction of iodate takes over, that is, it becomes predominant, and but has the same end product as non-radical reduction. So this is the non-radical scheme. Okay. This is the non-radical scheme, and this is a radical scheme. So when I minus is low, okay, so the radical reaction is like this: IO3 minus plus HiO2 plus H plus, giving rise to IO2 dot plus water, then IO2 dot plus Mn2 plus, giving rise to this, and since HiO2 is produced more than it is consumed, the rate of the above 2 steps increase as they occur. Okay, and therefore much more HOI is formed from reaction 8. Okay, so more of this is formed, because when this is low, this radical reaction is predominating, and Mn2 plus is oxidized in reaction 7. You see, it is 2 and this is plus 4 step. Okay, providing a means for the reduction of IO2 dot to HiO2, and Mn4 plus is reduced in reaction 9 here. Mn4 plus is then reduced to Mn2 plus, giving rise to HOO dot. Okay, then this HOO dot gives rise to H2O2 and O2. So this is your radical scheme. Okay, this is your radical scheme. So this this Br reaction, the HOI produced in the radical process reacts with malonic acid as in reaction 5, this one, reaction 5, and the production of HOI from the radical process is faster than its reaction with malonic acid, and an excess of HOI builds up from this radical process. This excess HOI reacts with H2O2 in this particular step, HOI plus H2O2, because it is excess, because it is less consumed. You see here this HOI generated here, it is less consumed. So concentration of HOI is increasing. Since it is increasing, the third step is again promoted. Okay, and iodide is produced. So build up of I minus shifts off the radical process and returns the system to slow non-radical process. as we have seen initially. Okay. So, as I minus is more, because you see in step 3 this I minus is again generated. Okay. When abundance of I minus is there, these steps are predominating. When I minus is less, then radical steps are predominating. Okay. So, as a result of which, at one time low I minus radical process, high I minus your non-radical process. So, these are changing from one situation, one mechanism to another, depending on the concentration of I minus. And what about the color change? Color change is like this: the reaction of HOI and malonic acid is a sequential one. I minus plus HOI, this step, 11th step, it is giving I2 plus H2O in presence of an acid. Okay. So, this I minus is an amber colored one. Okay. This I2 is amber colored. This I2 reacts with malonic acid, producing iodo, 2-iodo malonic acid, okay, and giving rise to I minus. So, amber color is the I2 produced in reaction 11. Okay. Now, the dark blue color is from I3 minus complex with starch. Okay. So, when I minus is greater than HOI from reaction 3 with H2O2 causes slower non-radical processes to take over, and the color fades as I2 is consumed. By reaction 12, you see I2 is again consumed. Okay. So, amber colored initial solution is as a result of I2, formation of I2, and this dark blue color in presence of starch is because of the formation of I3 complex. Now, this I3 complex will be more if I minus is more, okay, because I3 is formed as a result of reaction between I2 plus I minus. So, when I minus concentration is less, then I3 complex, that is the color of the starch color, is diminished. Starch, I mean in presence of starch, this blue black color is dark blue color is diminished. Okay. So, depending on the concentration of I minus and depending on how much iodine is produced, the color will switch from amber to dark blue and again dark blue to amber. Okay. So, if we look into the reaction scheme, okay, if we look into the reaction scheme, you see that there are two processes. Okay. One is favored by I minus. When it is process 1 is favored, you see, favored by low I minus. So, low I minus means when low I minus, then radical step, radical steps are prevalent compared to non-radical one. Okay. And when there is an abundance of I minus, then your these steps are prevalent. So, process 1 low I minus, that means radical one, and process 2 favored by high I minus. Okay. So, for this BR reaction, we can classify the situation in terms of the concentration of I minus, whether I minus concentration is high or I minus concentration is low. So, process 1 is prevalent when I minus is low. So, I minus is low, that means it consumes HOI slower than it is produced. Okay. So, HOI is built up. When HOI is greater than I minus, because you see low I minus, then I minus to I2 is produced, okay, that is amber colored, and HOI to I minus. Okay. So, the moment it is amber colored and this is producing I minus, so it slowly increases the concentration of I minus. Okay. So, let us again go back to radical steps. okay, that in radical step you see that when I minus is low, so HY is generated. So HY is generated means more HY means this one, this step will take place, okay. More HY means more this one, and more HY means again you see in presence of H2O2 more I minus is generated, okay. So HY more means this step is again prevalent even though for your radical process. So that is why we have written over here I minus to I2 and also HY to I minus, and then as a result of which, as a result of this particular step, I minus tends to increase, the concentration of I minus increases. The moment it is increasing, what is happening? That this process is taking over this process. So then non-radical process is prevalent because concentration of I minus has become high, okay. So in presence of high iodide concentration, non-radical process, that is these steps are prevalent, okay. IO3 minus plus I minus plus 2H plus giving rise to HiO2 plus HOI, hypoiodous acid, IO2 minus plus I minus giving rise to 2HOI. So these steps are prevalent. So when high, because you see these two steps are requiring iodides, that is why. So high iodide, these steps are promoted, more I minus requirement, although here one iodide is released, but you see consumption is more than the release, okay. So the process 2 is favored, okay. So it consumes HOI faster than it is produced in process 2, although in other case what is happening, that HOI is consumed slower than it is produced, but here HOI is consumed faster than it is produced, okay. So what is happening, HOI is reduced. So when HOI is, although in other case you see HOI is building up, here HOI becomes deficient, I mean HOI concentration is reduced as a result of high iodide concentration. So that means when HOI is less than I minus, that is high iodide concentration, then I minus plus I2 plus starch giving a dark blue complex, okay. And again by this I minus is decreased, okay. So the I minus is decreased means again we are now switching over from a high I minus zone to a low I minus zone. So what is happening, the system is transferred from here to here. So in this region to this region, back to process 1. So again your radical steps are favored. So you see that reaction goes this way, giving rise to amber colored. When I becomes high, is transferred to process 2, giving rise to your starch blue complex. So amber to blue transition, the moment blue is generated, again it is transferred to here, again amber colored. So this way it is oscillating like this, okay, oscillating like this, okay. So this way you can, we can explain why this color is changing, okay. Okay. Next we move on to the other case, that is Belousov-Zhabotinsky reaction. So BR reaction, this is one oscillatory reaction where we are having two color stages, one is amber, another is blue, but in case of Belousov-Zhabotinsky reaction, it is a multicolor, 4 color situations, okay. Now in this case, like your BR, there are 3 solutions required. One is 0.23 molar KBrO3, these numbers are best optimized mixtures. B is 0.31 molar malonic acid and 0.59 molar KBr and the C solution is 0.019 molar steric ammonium nitrate, okay, and 2.7 molar sulfuric acid and spiked with Faroan solution as indicator. Faroan is nothing but 110 phenanthrolene ferrous sulfate complex. It is a blood red color, Faroan indicator. Okay. So, like Br, let us go back to Br again. What was the there were also 3 solutions. It was spiked with 1% starch solution. There are 3 solutions, and here we are also having 3 solutions. Okay. Now, Belousov originally used citric acid as instead of malonic acid. It was later found that a number of different carboxylic acids could be used, and in place of citric acid you can use other carboxylic acids as well. Also, manganese ions could be used instead of cerium ions, and the overall reaction is cerium catalyzed oxidation of malonic acid by bromate ions in dilute sulfuric acid. So, overall reaction is this. Okay. So, what is the overall reaction? The overall reaction is represented here. Your malonic acid, bromate giving rise to bromide, carbon dioxide and water. But looking at this equation, we cannot say anything about this color change scheme. Okay. So, this gives you the overall mass balance, but this equation cannot explain why the color is changing. That is, the details of this reaction, details of this reaction is not understandable from this scheme. So, this equation does not account for the color changes seen in the reaction, the catalytic effect of cerium ion and the role of bromide ions. Okay. So, this is a gross equation which cannot explain all this. Again, the mechanism involves 2 different processes. Process A, ions and 2 electron transfer. Process B is radicals and 1 electron transfer, like Br reaction. In one case it is promoted by non-radical, another case it is promoted by radical processes. So, in the same way here, process A, ions and 2 electron transfer, process B, radicals and 1 electron transfer, and concentration of Br ions, Br minus ions determines which process is dominant. Okay. Like in other case, okay, your like here iodide concentration, when low process 1 is favored, when high process 2 is favored. In the same way here, when high Br concentration, process A, that is 2 electron transfer and ions, okay, ion process, and 1 electron transfer radical process with low Br concentration. Okay. Now, process A, net reaction BrO3 minus plus, process A means ions. Okay. So, BrO3 minus plus 5 Br minus plus in presence of acid giving rise to Br2. So, this is a reduction of bromate ions by bromide ions in 2 electron transfer process. So, it is a bromate bromide reaction giving rise to bromine. It is a typical happening also in case of iodate iodide reaction. Okay. And this reaction occurs when A and B are mixed. A and B are mixed. This bromate, bromide. Okay. This process occurs through this the following 3 steps: bromate, bromide, H plus, HBrO2 plus HOBr, then HBrO2 plus Br minus giving rise to HOBr, HOBr plus Br minus giving rise to Br2 and H2O, all in presence of acid. Okay. So this happens to through 3 steps as written over here. Okay. And what about malonic acid? Now, this malonic acid exists mainly in diacid form, but it slowly enolizes to this, although predominantly it is in acid form, but a little fraction of it may be in this form. So, enol form, and this enol form reacts with bromine to produce 2-bromo malonic acid. Okay. And these reactions together reduce the concentration of Br minus in the solution. Okay. So, this is one reaction, and this one another reaction. So, that tends to reduce the bromide concentration in solution. Okay. So, once process A has consumed most of the bromide ions, process B takes over. Process B means what? Process B means low bromide concentration, radical reaction and 1 electron transfer process. Okay. So, the overall reaction again is like this: BrO3 minus plus 12H plus plus 10 Ce cerium, ceras ceric system it is, giving rise to Br2 plus 6H2O plus 10 Ce4. Okay. This process is composed of the following steps 1, 2, 3, 4, 5. Okay. So, one is like BrO3 plus HBrO2 giving rise to BrO2 dot, BrO2 plus cerium 3 plus giving rise to ceric, then HBrO2 plus HBrO2 giving rise to HOBr plus BrO3 minus, that is BrO3 minus again comes back, then HOBr giving rise to HBrO2 plus Br minus, and HOBr plus Br minus giving rise to Br2. So, this is a complicated scheme, and of these first two steps involve radicals. Okay. So, when bromide concentration is less, so the process B predominates, that is, when most of the bromide is consumed. So, these 3 steps can no longer take place, or even if it happens with a very slow kinetics. Okay. So, the net result is, means if we combine equations, we get 2 Ce3 plus BrO3 minus plus HBrO2 plus 3H plus giving rise to 2 ceric plus water plus HBrO2. Okay. So, this sequence produces HBrO2 autocatalytically. Okay. So, autocatalysis is an essential feature of this reaction, but does not continue until the reactants are depleted, because there is a second order destruction of HBrO2 in reaction 10, this destruction. Okay. So, reaction 11, 12 represent the disproportionation of hypobromous acid to bromous acid and Br2. Okay. Reaction 11 and 12, this is number 11 and this is number 12. So, these two represent your disproportionation of hypobromous acid to bromous acid and Br2. So, it is basically a very complicated situation as you look into the expressions, that is whether it is a catalytic, it is a radical reaction or it is non-radical reaction, ion reactions, but it is a very complicated situations, and one is connected to the other by some feedback mechanism. That is means in one case when bromide is less, then the other step is promoted, I mean the other radical step is promoted. So basically they are connected, these steps are connected by nice feedback mode, feedback mechanism. Okay. Now Ce4 plus and Br2 oxidize malonic acid to form bromide ions. Once this concentration of Br minus becomes high enough, the process A is reactivated. Okay. So means in case of process B, when we started to talk about process B, we told that when Br minus is less, but now if we go back to here, you see here Br minus is generated. Okay. So that means Ce4 plus and Br2 when oxidizes this malonic acid, then again Br minus is generated. So this way, so basically what is happening, that you see that C4 is generated, steric ion is generated. This steric ion along with the bromine oxidizes your malonic acid and thereby generating Br minus. So when Br minus is generated, so slowly Br minus builds up, and when Br minus is built up, then again process A is reactivated. Okay. So automatically with Br minus concentration, process A is reactivated. So again go back to process A. You see here, this is your process A. So it requires Br minus. So these steps are again prevalent. So this way, at one time process A is prevalent, in other time process B is prevalent, like we talked about with Br reaction, process 1, process 2, depending on whether high iodide concentration or low iodide concentration. Okay. The similar is the situation, you see that here Br minus is the determining factor, and in this step Br2 oxidizing malonic acid to the corresponding bromo derivative, and Br minus is generated, that is brominating your malonic acid and thereby generating Br minus. Once Br minus is generated, then process A is reactivated. So this way back and forth, means one time process B, another time process A. So it is switching from B to A, B to A, and correspondingly color will also change. So we will come to that. Okay. We will come to that. Okay. So what is the role of Faroan? Faroan is the indicator, ferrous orthophenanthrolene complex. Okay. So how these colors are coming? As cerium 4, that is steric ion, increases, it oxidizes iron, okay, iron 2 of Faroan to iron 3 of Faroan. I mean oxidizes iron 2 to iron 3 in phenanthrolene complex. So iron 2 in phenanthrolene is red and iron 3 in phenanthrolene is blue. Okay. So basically there is a changeover from red to blue, okay, and maybe blue to red, and steric ion is and correspondingly steric ion is reduced to serous, that is cerium 3, it is a colorless, and cerium 4 is yellow. So the combination of yellow and blue, okay, so cerium 4 yellow and iron 3 blue, okay, this combination makes the green color. Okay. So the oscillating concentrations and oxidation states of iron and cerium accounts for the color change. Okay. So now we can explain the color change. Okay. In both Br reaction and in Bz reaction, although for Br case it is it's a simpler situation, but for serous, steric and Bz reaction, it's a combination of you see red, blue, then yellow, and depending on how much of red, how much of blue and how much of yellow is present. So, accordingly the color will change. Okay, accordingly the color will change. So, this the oscillating concentrations of here the deciding factor is bromide, and the various oxidation states, one is iron 2, iron 3, another is ferroceric. Okay. Then the various oxidation states of bromine also. Okay. These are responsible for switching of color from one to another. Okay. Now, why do we need to study such things? Is it just for laboratory curiosity, or just for having fun with chemistry, or it has got some extra significance? Okay. Now, oscillating reactions are much more than laboratory curiosity. They are known to occur in some industrial processes, and there are many examples in biochemical systems where a cell plays the role of a chemical reactor. Okay. So, cells are nothing but small chemical reactors, okay, basically biochemical reactors. Now, oscillating reactions, for example, maintain the rhythm of heartbeat. Okay. They are also known to occur in the glycolytic cycle, in which one molecule of glucose is used to produce, through enzyme catalyzed reaction involving ATP, 2 moles of ATP. Okay. So, it is important there. All the metabolites in the chain oscillate under the same conditions and do so with same period, but with different phases. Okay. So, this oscillatory reactions, although BZ reaction and BR reaction, these demonstrate the apparent anomaly. Although it is not an anomalous thing, apparent anomaly means if you look into these colors, it looks something anomalous. That why chemical reaction this color will come back, it looks like as if your reactant is regenerated, but chemical reaction should not, in case of chemical reaction, that should not happen. Okay. So, it is contrary to our general understanding and simple minded understanding, but it happens. So, basically if you can design a reaction or maybe a number of reaction steps in such a way that they are interconnected, and if you optimize the concentrations of the reactants in such a way that one reaction acts as the feedback for the other reaction, that is, I mean, when some concentration is reached, I mean concentration of one reactant has reached certain limit, then maybe second reaction starts, and the second reaction again what it does is that again reduces or increases the concentration of that particular component, like say in case of Br it is iodide, or in case of Bz it is bromide. Okay. So, if they are interconnected, then you can simply play with different colors. Okay. So, so basically the importance of studying is that of such reaction is that it is apparently something we do not we cannot, maybe it looks like that as if it is contrary to our general understanding. That is why you see that Belousov's paper was rejected, because people did not have the idea at the then time that such situation may be possibly reached. Otherwise, maybe Belousov might not have left science, and who knows that he could have given us more interesting things. So, and also the important point is that as I told you at the very beginning that two or more autocatalytic steps, if these steps are involved in some reactions, then we may get oscillatory reaction. And if we look into the concentration of species, different species, you see that they are oscillating in time and there is a phase lag. You see its maxima is here and the green maxima is here, okay, because maybe the green substance is generated out of red substance. So, when red substance is maximum, then green is maybe minimum, and then when as with time green is red is depleted, green is generated. So, they are interconnected. So, that is why when we think of autocatalysis reaction and two or more autocatalytic steps are involved in a particular reaction, we can get such a nice oscillation of colors. It is basically a chemical oscillation, but the thing is that these reactions will not occur for infinite period of time. At some point of time it will stop oscillating and a true equilibrium will be reached. True equilibrium means when there is no further color change. Okay. So, no further color change, and it is basically it will be showing some damping pattern. Initially the color change will be very distinct, and later on with time this color change will be damped, like a damped oscillation, because ultimately for your, say, as I told you, for your BZ reaction, malonic acid when gets oxidized by bromine produce bromide. So, bromide, when high bromide is there, then the process A is produced. Process A means this one, that is non-radical reaction is promoted. Okay. So, malonic acid, you have got concentration of malonic acid to a fixed value. So, during the course of reaction the concentration of malonic acid is reduced. So, reduced and ultimately it is maybe exhausted. So, when it is exhausted, then what will happen, that further reaction to produce bromide ions will not be there. Okay. So, that is why the thing is that ultimately the reaction will stop at some point of time. Okay. So, what have we learned out of this? Before that, I must say one thing, that students are encouraged to try this reactions. Okay. Maybe if proper safety precautions are there, then you can try, because sometimes sulfuric acid may be dangerous. So, I recommend that you get in touch with your teachers, or maybe some chemical laboratory, or maybe some research laboratory where these reactions can be carried out with maintaining the proper safety issues. Okay. So, like for Br reaction, you can get H2O2, KiO3, H2SO4, malonic acid and MnSO4, and 3 solutions. If these three are mixed, and if you put a little amount of starch, then you will be getting this color change from amber to dark blue, and then dark blue to amber, and so and it will oscillate with time. In the same way, for your Belousov-Zhabotinsky, if you use this, you can get nice colorations. Okay. So, basically the color for your BZ reaction, there are 4 colors, because depending on, as I discussed, that depending on the concentration of various colored substances, you will be getting different colors. Okay. So, what have we learned out of this, out of this discussion? That autocatalysis is a key point, and more than one autocatalytic steps are very important, okay, for such oscillatory reaction to be observed. Okay. Autocatalysis means your product, once your product is used up as reactant. So, the more product, more reactant. So, reaction is enormously with high rate. Okay. So, when there are more than 2 or more autocatalytic steps, you can get such oscillation of concentration and correspondingly oscillation of color. If you have a typical indicator, means corresponding indicator like Faroan or maybe like your starch, as I discussed with your Br or Bz reaction. And history is like Belousov-Zhabotinsky Br reaction. So, these are commonly demonstrated oscillatory reaction, and Belousov in 1950 discovered this particular reaction, but unfortunately people or scientific community did not accept it. Later on it was established by Zhabotinsky, that is why it is Belousov-Zhabotinsky reaction, and there is another reaction which is Br reaction, Briggs-Rauscher reaction. So, that is also an oscillatory reaction, and we have discussed in both the cases, like in Br as well as Bz reaction, it has got non-radical, and one is free radical step, another is non-free radical step. Free radical step one, this is a free radical, non-free radical one, another is radical one. So, both reactions are going through radical as well as non-radical pathways, and depending on the concentration of iodide for your Br reaction, when abundance of I minus is there, then your non-radical channel is opened up, and for your radical step, when the concentration of iodide is low, then radical step is prevalent. Okay. Next is and we have tried to explain why this color is shifting from one to another, why the color is shifting from one to another, and it depends on the concentration of I minus, and when concentration of I minus is low, then this amber color is produced. When concentration is high, then is blue color is produced. So, with this diagram we have been able to we have explained it nicely. Then we came to Bz reaction, and like Br reaction, it has got this process A and process B. Process A is a non-radical ion reaction with 2 electron transfer, and process 1 is a radical reaction with 1 electron transfer. And here malonic acid is a very important ingredient, and this color is because of this cerasteric and ferraspheric system, as I explained over here. And ferraspheric Faroan form of ferraspheric gives different colors like red to blue, and cerasteric is yellow, ceras is colorless. So depending on the concentration of iron 3 and iron 2 and also cerium 3 and cerium 4, the color is visible, different colors are visible. So these oscillatory reactions are very important, not only in laboratory perspective but also in your biochemical cases, maybe living system. These are very important. So with this today I would like to conclude. So thank you for your patience. Goodbye.